In this session, we are going to discuss about transformation of state model. See, the state model of a system is not a unique model. We have gone through different modeling using physical variables, phase variables or canonical variables. So, in the case of state model using physical variables, they are very useful because they can be measured and can be used for control purposes, because we have discussed about one problem, that is we can represent the state model by using electrical components such as resistors, capacitors and inductors. So those are physical variables. Okay, so the voltage across capacitor, inductor or current through the capacitor or inductor are physical variables. So they can be measured and it can be used for control purposes. But the state model using these physical variables is not convenient for investigation of the system properties. So we are using another model, that is canonical state model, because it is very convenient for time domain analysis. In all these methods, we are using a system matrix A, because we are representing x of t will be equal to x dot of t equal to a into x of t plus b into u of t. That is our state equations. So in the case of canonical method also, the matrix A is representing the system matrix, and here in the case of canonical model, A will be a diagonal matrix, that we have gone through in the video classes, that it is a diagonal matrix. Therefore each component state variables equation is a first order equation, and it can be obtained from other state variable equations. So when the system matrix A is not a diagonal matrix, that is if it is a non-diagonal matrix, and it has if that matrix has distinct eigen values, then it can be converted into diagonal matrix by a transformation using model matrix. So once again, suppose the system matrix A is a non-diagonal matrix, then the eigenvalues corresponding to that matrix can be converted into diagonal matrix by a transformation using model matrix M. So any system matrix can be converted into other state model by using model matrix M. That is the point here. So we will go to the model matrix and all in the next slide. So that is, the state model is transformed into canonical form by using the model matrix M. So when the non-diagonal system matrix A has a multiple eigenvalues, it can be converted to Jordan matrix by a similarity transformation using the model matrix M. See, here we are discussing two cases. That means if this state model system matrix, that is, we know that in the case of state modeling, we are representing x dot will be equal to a into x of t plus b into u of t. In that, A is called a system matrix, and if that system matrix is always in the case of canonical form, system matrix will be a diagonal matrix. But if it is not a diagonal matrix, then we can convert that into a diagonal matrix by using the model matrix M. Okay, so we are, in order to find this model matrix, we are using eigenvalues or eigenvectors. You know about eigenvalues of a matrix. See, when we are taking the characteristic equation, that is determinant of lambda I minus a, if A is a matrix, then its eigenvalues will be lambda I minus a, determinant lambda I minus a equal to 0, then the corresponding roots of lambda values will give the eigenvalues or eigenvectors. So by using those eigenvalues, we are making this model matrix M. So if a system matrix is not in the canonical form, we can convert it into canonical form by using model matrix. So if we are calculating this eigenvalues, when these eigenvalues have multiplicity, that means one eigenvalue is repeating, then the procedure to find the model matrix is different. So we are using another type of model matrix, okay, that we will discuss in the next slides, okay. So by using this method, we will be getting another canonical model, but that is Jordan canonical form. So let us see the transformation. So canonical form of state modeling, we will discuss about the canonical form of state modeling. Suppose we have a system and it is represented by the state variables like this. See, x dot will be equal to ax plus bu. That is the ordinary representation, that is state space representation by using state variables, where x is a state variable and its order will be n by 1. That means n rows will be there and 1 column will be there. And if we are representing it by a new state variable, suppose that variable is z, then z will be related to x. Here we are using x is the variable. Now we are representing the system by using another variable z. Then corresponding z and x relation will be x will be equal to m into z, where m is the modal matrix. Okay. So here we are assuming that A is not in the order of a diagonal matrix. Diagonal matrix means that diagonal entries will be 1. Okay. That is a diagonal matrix. Okay. Or diagonal entries, sorry, that is unity diagonal matrix if the diagonal, all other entries except the diagonal elements will be 0 in the case of diagonal matrix. That means diagonal elements will be non-zero in the case of diagonal matrix. Okay. A unity diagonal matrix means that diagonal elements will be 1 and all other elements will be 0. So that is a diagonal matrix definition. So once the system matrix is not a diagonal matrix, we are using a transformation, that is x will be equal to m into z, where m is the modal matrix or diagonalization matrix, and this is used to diagonalize this matrix A. For that we are using a transformation, x will be equal to m into z. That is the thing here. Okay. So here we are representing the system by the state equation x dot equal to ax plus bu. And output equation will be y equal to cx plus du. You know that u is the input. Okay. Similarly, we can say that when we are substituting this x equal to mz, we will get a x dot. First equation will become x dot equal to, instead of ax, we will get amz and bu will be same. Y equal to c into mz plus du. So these are the two equations when we are substituting x is equal to mz. So if we are multiplying this relation by m inverse quantity, so we will get at the left side m inverse x will be equal to m inverse amz plus m inverse bu. And the relation governing x and z, we know that it is x is equal to mz, that we have taken. So now we have this form, and if we are differentiating this equation, that is this equation, we will get x dot will be equal to m into z dot. And if we are multiplying this equation by m inverse, we will get m inverse x dot will be equal to z dot, right? So that is this equation. So instead of this quantity, we can substitute z dot. So we will get z dot will be equal to m inverse am z plus m inverse bu. That is the equation here. And here m inverse am is represented by this symbol, and it is called a Gramian matrix. Remember this equation because it will be useful for doing problems. That is, m is a modal matrix, A is the system matrix, m inverse am will be equal to Gramian matrix, and it will be useful for doing problems. So remember this. Okay. And here m is the modal matrix, and similarly in this equation there is m inverse b. So we are representing this quantity by b cap, and also when we are taking the output side equations, we will get z into m, that is will be equal to c cap. So initially this state equations will be x dot into ax plus bu. Now it become, what is, in terms of z, it will become z dot equal to Gramian matrix into z plus b cap into u, and y will be equal to c cap into z plus d into u. So now this is our new equations. Okay, so this equations, that is 5.41 and 5.42, represents the new state equations, and here the matrix will be, system matrix will be transformed to canonical, system matrix will be transformed to diagonal matrices. So this represents a canonical form. See, this idea will be clear when you are doing problems. So by using the modal matrix, you will get a diagonal matrix. That is the point here. So now we have a question, that is, how will you get this modal matrix? So modal matrix M will be obtained from the eigenvectors or eigenvalues. So these eigenvalues will be obtained from the characteristic equation. We know that in the case of a system matrix A, here In the question you will be given the system matrix A. So once you get the system matrix, the corresponding eigenvalues is obtained by determinant lambda I minus A equal to 0. So that equation will give you the different eigenvalues such as lambda 1, lambda 2, lambda 3, etc. So from that eigenvalues you will getting model matrix. So if you are representing, if this is the model or system matrix that you have obtained from the question, and in this case see, this is, you can see here that this is in the form of companion or bush form that we have discussed in the previous first classes videos, because in this case the lowest line or last row represents the negative of the coefficients of state variable matrix, and all other entries, first entry will be 0, first column entry up to the last row will be 0, and other entries will give you a diagonal matrix. You can see here the unity diagonal matrix, the diagonal elements will be 1. So this is in this type of matrix is called a companion or bush form. And when you are having this, and you have got different eigenvalues by using the characteristic equation, then the matrix, model matrix is obtained by from that eigenvalues will be represented in this manner. See, 1 1 1, and now you have different eigenvalues obtained from the characteristic equation. Then you can represent the model matrix by putting lambda 1, lambda 2, lambda n. In the next row it is lambda 1 square, lambda 2 square, lambda n square. The last row it is lambda 1 raised to n minus 1, lambda 2 raised to n minus 1, etc. up to lambda n raised to n minus 1. So this is the way we are getting the model matrix when the eigenvalues are distinct values, distinct n values. That means there is no repetition of any eigenvalue. Then the model matrix obtained is also called, what is called, Van der Monde matrix. Okay. So this is the way we are obtaining this model matrix. And once you obtain this transformation such as z equal to x mx, then you will get z dot will be equal to Gramian matrix into z plus b cap into u, y will be equal to c cap into z plus du. So this is the state equation for this canonical form transformation, canonical model. Okay. So you remember this state equations. So this is the state equation and this is the output equation, and all together this represent, that is state equation together with output equation represent the state model for a canonical form. Okay. So this represents the canonical model. So this is the equation corresponding to canonical model, and in this case how will you get this? You will get it from the transformation. Here the transformation used is, you can see here, that is x is equal to mz, which is the transformation we have used, and you will get the model matrix in this method when the eigenvectors are distinct. So there is another case when if there is a multiplicity of eigenvector, then that we will discuss next case. So in that case, when you are making substitution, we will get a Jordan canonical form of state model. So let us see the discussion. So if the eigenvalues have a multiplicity, that means one eigenvalue is repeated, then the canonical model system matrix cannot be diagonalized, and we will represent the corresponding state model is called a Jordan canonical model form. And the corresponding state equations is given by z dot is equal to jz plus b cap into u, and y equal to zz plus du. So here there is a difference j. Here j will be equal to m inverse into am, and b cap equal to m inverse b, that is similar, and c cap equal to z into m. So here the notation and difference is only for j. So that means j is obtained by using another model matrix. So if the eigenvalues have repetitions or multiplicity, then the model matrix is taken from another way. Let us see. So if the multiplicity, suppose q number of eigenvalues are repeated, then we will have, in the case of Jordan matrix, there will be a block that is having order q by q order. That means q number of eigenvalues are repeated. So a section of the Jordan matrix will contain that is section means q by q order matrix will be representing the Jordan block where the eigenvalues will be repeated. Here we are using lambda 1, lambda 1, lambda 1. That means q is equal to 3. That means this eigenvalues or eigenvectors are repeated. So this represents the Jordan block of size 3 by 3, and all other entries you can see that all other entries are distinct eigenvalues such as lambda 4, lambda 5, lambda n, like that. Okay. So now we have a system matrix with eigenvalues lambda 1, lambda 2, etc. up to lambda n, and lambda 1 has a multiplicity of 3. Then the Jordan block for this case is given here. Okay. So here the Jordan J represents the Jordan matrix, and okay. Now we want to know how we can write the modal matrix when the eigenvalues are repeated, and this is the way we can write the modal matrix. See, in this case we are writing it as in the first column all other entries you can see first is 1 and other entries are 0, and first other entries will be lambda 1, lambda 1 square, lambda 1 cube, like that, lambda 1 raised to n minus 1. Okay, and in the case in the second row it is second element is 1, next element is 2 lambda 1, 3 lambda 1 square, like that. See, this is the way we are representing the modal matrix in the case of multiplicity for eigenvalues. Okay, so this idea will be clear when you are doing a problem. Okay, and here you can notice one thing, that here lambda 1 is the eigenvector or eigenvalue which is having the property multiplicity. That means it is repeated q times. Okay, so that is why it is represented like lambda 1, lambda 1 square, lambda 1 cube, etc. up to lambda n minus 1, and lambda q is also repeated. You can see here that. Okay, next is the computation of the state transition matrix by the canonical transformation. See here, this, we are directly going to the state transition matrix equations. So because for the examination purpose you will be asked for finding the state transition matrix. So state transition matrix, we know that its representation is e raised to at or phi of t, and it will be obtained from the modal matrix as m into e raised to Gramian matrix into t into m inverse. So in the case of finding the state transition matrix, you have to find out m value, also you have to find out gamma or Gramian matrix. So you should know what is this Gramian matrix. So m is the modal matrix and Gramian matrix is obtained. Here it is e raised to gamma t, where e raised to gamma t is obtained by e raised to lambda 1 t 0 0, that is it is diagonal elements is e raised to lambda 1 t, e raised to lambda 2 t, etc. up to e raised to lambda n t, where lambda 1, lambda 2, lambda n are these all are eigenvalues or eigenvectors, and these eigenvalues are obtained from the roots of the characteristic equation, that is lambda I minus a, where a is a system matrix that you will be given in the question. And here we have in this is a state transition matrix corresponding to eigenvalues which are distinct eigenvalues. When if there is some of the eigenvalues are repeated or the eigenvalues have a multiplicity, then the corresponding state transition matrix is obtained by the equation e raised to at equal to m into q of t into e raised to Gramian matrix into t into m inverse. So e raised to gamma t is obtained by the same equation. In this case, the sum of the gamma 1 will be repeated. Okay, gamma will be repeated, sorry, lambda will be repeated, and here q of t is obtained by the equation by this matrix, and you it will be little confusing. You will be getting the idea when you are when we are discussing a problem. So let us do in the a problem in the next case. Here you should remember one thing, that how we are forming a modal matrix to get the modal matrix in order to get the state canonical model. So in the first case, if lambda, that means eigenvalues are not repeated, then modal matrix is obtained directly from the eigenvalues by using this matrix. And if the eigenvalues are repeated, that means suppose q number of eigenvalues are repeated, that means here it is represented by lambda 1, that is it is repeated q times. So up to q columns it is the same, like repeated like this, but after the q plus 1th column, it will be going like this. Okay, going like this means it is similar to the previous model matrix, that is lambda 1. At the first case it is lambda n, second case it is lambda n square, like that. You can see here also, after the q, the other eigenvalues are not repeating, so you are writing lambda q plus 1 here, lambda n here. Next row, lambda q plus 1 square, lambda n square. Next, lambda q plus 1 cube. So this represents eigenvalues are not repeating, and up to this section, this notation represents that eigenvalues are repeated. That is why we are using this notation. Okay, so let us do a problem.